Alright, so this is lesson 1.09, the first of 2 lessons that are on the 1.11 quiz. And we are going to cover actually 2 more laws, but really the strong focus is on the ideal gas law. Alright, so, but quickly before we start on that, I want to go over the combined gas law. So this one is helpful when you have maybe multiple things changing. Alright, so this takes our 3 gas laws that we've already talked about and combines them together. Alright, because you can see on the top of the parentheses, alright, up here, that looks a lot like our Boyle's law. Alright, or if you look here, that looks a lot like Charles' law. Or if you look here, that looks a lot like Gay-Lussac's law. Alright, so this is really just these 3 laws combined into one law. So, and this helps you if you ever have a question like this one. Alright? You must convert 10 liters of nitrogen gas from a temperature of 300 Kelvin and a pressure of 203 kPa to STP, or standard temperature and pressure. This is where they love to make sure you remember what value standard temperature and pressure were. Alright? So, this question is maybe a little unclear, but I'm going to add just a little bit of detail. So we're going to have to figure out what the new volume is. Alright, so we know our starting information. 10 liters, 203 kPa, 300 Kelvin. Alright, so we've got V1, T1, and P1. Our ending information, alright, is coming from here. We can get P2 and T2 out of STP. Alright, pressure is going to be 100 kPa. And temperature is going to be 273 Kelvin. Because those are your values for STP. That's why you want to remember these. So, and if you don't remember these, this doesn't sound familiar at all, go back to the very first recording. So this is a combined gas law problem. So we've got P1 V1 over T1 equals P2 V2 over T2. So let's plug in what we know. Our starting stuff is 203 times 10 divided by 300. That's the actual temperature there. And that's going to be equal to, I know P2 is 100. I need to solve for V2. And my new temperature is 273. Alright, so let's simplify things a little bit here. 203 times 10 divided by 300. So this is going to be equal to 6.77. And then 100 divided by 273, which is going to be 0.37 V2. So I'm going to divide both sides by 0.37. 0.37. That cancels there. Need some more space. So 0.77 divided by 0.37 is equal to 18.3 liters. Alright? So the ideal gas law. So this is your ideal gas law. This one's a little bit more complicated than the other ones. Pressure, volume, and temperature are in there. So are moles. Alright, so the N stands for moles. There is also this constant. So it's a number that just makes this equation work. But you'll always have to remember to put this number in there, to make the equation work. Alright, which version of this R proportionality constant that you use depends on the pressure units. Alright, if you're using kPa, you use the 8.31 version. If you're using atmospheres, you use the 0.821 version. Alright, so your temperature needs to be in kelvins when you use this, just like it needs to be in kelvins for all the other questions. We haven't actually covered how to convert to Kelvin yet, so don't worry, for now you're still going to get everything in kelvins. Just keep that in mind when you hit the unit test and we've covered everything. So, pause this if you're still writing the equation. Alright, so using your ideal gas law. If the temperature is 300 Kelvin, the pressure is 120 kPa, and you have 12 moles of gas, what must the volume be in liters? Alright, so let's identify what we know. We've got 300 Kelvin, 120 kPa, 12 moles. So, Kelvin is temperature, kPa is pressure, moles is the N, and then what we have to solve for is volume, so that's our question mark. And again, this is, especially if you see moles, that should automatically make you think, ideal gas law. So it's PV equals nRT. Alright, so let me plug in 120 times V, which we have to solve for, which equals 12 times, let's see, thinking about our constant, the 8.31 is the one that involves kPa, so that's going to be the one I use here, times 300. So I've got 120 times V equals 12 times 8.31 times 300, so 29,916. I'm going to divide both sides by 120. So our new volume, or sorry, not our new volume, just our volume, is going to be 249 liters. Kind of big, I know, but sometimes you deal with big amounts of things. Okay. So now that we've talked about the ideal gas law and practiced that, something to keep in mind and make sure you take notes on these are just the characteristics of an ideal gas, or the properties of an ideal gas. Real gases really don't abide by these. There are certain conditions where you can get a true real live gas to act like this, but like anything that you interact with normally doesn't actually abide by this. But ideal gases, we have to assume that the particles have negligible volume, that the particles, so this isn't that the gas has negligible volume, it's just that the individual molecules making it up have no volume. The particles of ideal gases are always in constant random motion. Alright, that might not be so hard to come up with, but there are quite a few times when something will kind of cause an attraction of some sort or another, which then makes it not so random motion. All collisions between particles of ideal gases with each other or containers are perfectly elastic, meaning no kinetic energy is lost. This is probably one of the hardest ones to make come true, because just inherently when things interact, kinetic energy is lost. And the particles of ideal gases in no way interact with each other. So, these are a list you want to know, but just know that this only applies to ideal gases, which are, again, kind of theoretical. or can happen but only under extreme conditions. So this you can practice by solving some of these. Alright, I'm actually I'll solve maybe the first one, but what I really want you to do is figure out which equation is going to help based on the problem. So, first one, you have 12 moles of gas, 200 Kelvin in a 5-liter container. What is the pressure? So, to me, if you haven't already, pause and try this on your own, but to me, this is what tells me which equation I need to do. This is a PV or an ideal gas law problem. So it's the only one that has moles in there. So a next one, a gas is held at 2.5 atmospheres at 300 Kelvin and a piston held at 5 liters. The piston is pushed down to a volume of 2.5 liters, but temperature rises to 400 Kelvin. What's the new pressure? So I've got a starting pressure, a starting temperature, and a starting volume. I have a new volume, a new temperature, and I need to solve for pressure. So what equation has all three of those things on both sides? That's going to be your combined gas law. So the P1 V1 over T1 equals P2 V2 over T2. Alright, so next one. How hot will a 2.5 liter balloon have to get to expand to a volume of 350 liters? Assume the starting temperature is 245 Kelvin. So we have a starting volume, starting temperature, an ending volume, and I need to figure out that ending temperature. So I need an equation that is just volume and temperature. That's going to be your Charles law, or your V1 over T1 equals V2 over T2. And last one, a gas has a pressure of 799 millimeters of mercury at 313 Kelvin. What's the temperature at standard temperature and pressure? Alright, so if you need to, write it out. You've got, what's the temperature at standard pressure? Alright, so standard pressure is one we know. That's going to be 100 kPa. Oh, and I apologize, I haven't actually, but that is 760 millimeters of mercury. You would be given that if this was a problem you had to do. So we know P2, P1, V1, or T1, T1. So this sounds like a gay Lassuck problem. P1 over T1 equals P2 over T2. Alright? So, and I did say I would solve one. If you got the solving part down, you don't need to necessarily watch this, but this first one, I've got 5 times pressure equals 12 times, let's see, so my R value, I can choose either one. That's just going to dictate what my pressure units will be. So I'm just going to use 8.31 times 200. So 12 times 8.31 times 200. I apologize that my handwriting got really sloppy at the end there. 12 times 8.31 times 200. Sorry, that just didn't seem right, but oh, I guess it was. So we have 5p equals 19,944 divided by 5, because that's what I'm going to have to do, divide both sides by 5. And you end up getting almost 4,000 KPA because that's what the units would have been on that R unit, 8.31. So again, if anything's not making sense, come get help. You can totally get through this. Just take your time, think your way through these, and keep practicing them with me.